which I pinched from a book by the master of one of the Oxford colleges, who that's his biography. And I'm an optimist as well, so I rather like the battle experience as an optimist, because I'm optimistic about formal methods. I think they're going to keep going. Everyone's certain that they're going to die out, but they haven't died out, and they're continuing. So, with the background, I've got a few silly slides. So, although this one isn't so silly, because in the early days of the Airbus going up, they really did reboot the software just before they took off, because they knew if they did that, they were less likely to have problems in the air. So that's one of the issues with software. We know that they can go wrong, and we want to find ways of it not going wrong. Formal methods is just one of those ways. Yes, now, in fact, formal methods have been applied in the Airbus and other aircraft, so it's particularly obviously useful in safety and security systems, especially I guess in aircraft, because there a lot of systems the best thing is just to shut down and stop an aircraft. That isn't the best thing to do. It's a rather dynamic system. I've actually had a go on an aircraft. It's just where it's a simulator. But I mentioned one of the things I do is travel around, so I have to do quite a lot of accreditation visits with somebody else in the audience here. Thank you very much for that. And one was actually at the Emirates Aviation College, which is the Emirates company that's flying to Dubai. And I guess when you go and do these accreditation visits, they just happen to have 3 simulators that they have for their practical sessions, which is quite a nice setup for practicals compared to what I got when I was a student. So at least they say, well, I need to go and test out the practical equipment to make sure it's all up to scratch. And actually, it's surprisingly easy to actually do the flying, taking off and so on. The difficult bit is actually switching the thing on. It takes about 20 minutes. It's not just turning the key. You have to power up the engines separately and make sure everything's okay. There's somebody just behind the person who took his camera and did all that for me. And then they just said, right, you can take off now. And then runs around and over the palm and Dubai and so on, and then back down again. So I mentioned one of the issues of academia and industry not mixing too much, and I guess that's really somewhat theory and practice not mixing. So one of my things that I'm very keen on is to actually get theory and practice working together. And it's just a nice quote that all the formal methods people here will have seen, but some of the others may not have seen. It was left by Christopher Strachey, who died rather young in Oxford, and left this note on his desk. Tony Hoare found when he arrived at Oxford. I think he uses it quite a lot. But certainly it's something that Tony Hoare and the rest of the group at Oxford have tried to promulgate, that you need to get the 2 parts together. It's not even the case in a lot of computer science departments that the theory and practice people talk to each other. So it's not just industry and academia. So of course, formal methods. Well, I've been asking this in every talk, where did the term formal methods come from? And nobody seems to know. I mean, we know where software engineering came from as a NATO event and so on. It seems to have come out of the mathematical world. I mean, I've certainly got a book with the title Formal Methods in the sort of early 60s about logic and so on by a mathematician. How it actually got into computer science is still an interesting, well, if anyone knows, I'd like to know. Formal methods, there are 2 parts. You can do specification proofs, and I put optionally there because actually a lot of use in industry is more on the specification end, which a lot of proof people are down on, but actually it's it's just as important a part of using formal methods. And I'd say, well, I'm an engineer by training, and I would actually say, software engineers trying to say engineers have to do proofs. If you try to say that in any other engineering discipline, they'd look at you and think, But yes, obviously theoreticians need to go and do that. Do the actual practical people need to do it. I'm coming here, I walked past the James Maxwell building in King's College, south of the river. He came up with Maxwell's equations, and now engineers all use Maxwell's equations, and we assume he got it right, he was a very clever person. We don't have to find or prove Maxwell's equations every time we need to use them. And I think for the future, if we're looking to developing software engineering, we really need to try and do the foundational proof work and so on, to try and make it a much more calculational approach once we've done that. One thing I've organised for a long time on the web is formal methods information. So I've managed to be reasonably high up on the Google rankings when you type formal methods. And more recently, I've set it up as a wiki. So anyone here who wants to put anything about anything you're doing with formal methods or find out about it, you're very welcome to go to this wiki site. And the notation I've used mostly through my career is the Z notation. I mean, there's lots of different notations, and I guess Z is getting a bit long in the tooth now. Most people, if you're starting now, a lot of people are using B, event B, and so on. But I'll use Z as a case study, because actually the big project I'm going to talk about, it was based on Z. So Z is still being used for real projects in industry. It hasn't disappeared. You may not hear about it. And that's one of the issues, is that in industry you have to sign non-disclosure agreements and so on. But there's one other person in this room who I can't reveal, who was on the project and so on, so you're not allowed to always talk about these things. But anyway, looking at Z notation as I guess how it's developed as a community, if you want to get a formal method accepted, you've got to put quite a lot of effort into community building for that method. And certainly a lot of effort was put in on Z. I mean, more recently, I've actually looked at this in the context of sort of a sociological view of how you develop a community. And when I was involved with it, I didn't realise that there were more theoretical ways of looking at it. But anyway, you certainly need to develop things like courses, and there are people in this very room who still teach Z courses, so there's lots of Z courses both in academia and industry. You certainly need textbooks. I mean, in Z we have a reasonable choice, but I think still, over the years, there's still only been, say, 15 Z textbooks. And if you go and sort of count the number of Java books, it's 1,000 Java books. So that sort of puts you in the context of where a formal method is compared to mainstream programming languages and so on. Nevertheless, probably Z has more textbooks than I think probably any other formal method. Tools are very important. That's the one area where perhaps Z hasn't been so good, and I'll come back to that, because an industrial project you expect tools. And talk about a project that used Z and made the best of what tools there are, but certainly tools could be improved. So newer projects like B and so on are better tools, and that's where you might start if you're starting from scratch now. So there's various web resources, discussion groups. We have a Z user group. There is a Z standard. I mean, that's one thing. If you do a new notation, you're probably going to want to do an ISO standard. Has anyone? I always ask, because somebody has been involved with standards. Anyway, so it's a long process, and certainly with Z, a decade was spent, and some problems were found in that decade, so it probably was worth it. Yes, the person who found out these problems is in this very room. So, there's a lot of effort involved. And literally, we had a specification of Z in the beginning of the 90s, and by early 2001 there, we come up with a standard, so it took a long time. But it is useful for tools and so on. So this is just, some of you have probably seen this in the formal methods people, but this is just thinking about abstraction, because actually formal methods and formality is about abstraction. What level are you going to describe a system at? So when you start to describe a system, you might literally have a back of an envelope to start writing things down. And you might go and talk to the customer and write some points of things they want. And I'm just surmising in this fictitious example that maybe you write 25 lines down talking to the customer, find out what they want for the system. And probably informally. And then you go back to the company or whatever, and you start thinking about what it really is they want. And if you're a Z person, you might try and write some little bits of Z specifying what you want. But you're probably going to flesh it out a lot more, come up with some sort of spec, and probably start finding sort of inconsistencies in what those requirements were, and go back and perhaps change those requirements. And you can see at this point, it's not too much complexity. It's fairly easy to change your mind. Then, of course, if you agree that we've got a spec, then you'll start trying to do a design where you're going to start saying how you're going to implement it with data structures and exactly the way it's going to be implemented. Yes, and I put these of orders of magnitude bigger each time because actually I think unless you have an order of magnitude more complexity in the next level, there's not much point in doing that. I have seen one formal methods paper where it had a spec and then it had a program. The program was, I think, 1.5 times as long as the spec, and the whole paper was written proving that one like the other. Well, I didn't think that's a particularly useful exercise. But if you're trying to connect things that are an order of magnitude different in size, then that's a useful exercise. So eventually, of course, you're going to try and program this, and that's where I say that everyone has to use formal methods because a program is a formal object. It's got a mathematical meaning. It just happens to be executable. It happens to be a lot bigger than what you need if you just write a specification. So, of course, at each of these levels, you'll probably find problems, and you'll have to go back. And you hope you don't have to go back all the way to the top, because that means you have to go all the way around bigger and bigger loops. So the more you can be doing these loops higher up, the better. Getting rid of errors. Obviously, errors are going to always seep down, but the more you can get rid of as you do this, the better. And of course, after that, it's all now you have compilers fully automated, like a big machine. So you'll be on something with millions of components once you're running. So of course, I'm interested in this talk in these upper levels, getting to the program code. So just a couple of silly slides, which some of you may have seen, but certainly trying to sell formal methods in the industry is a difficult. I don't know if anyone's tried selling eels. These are quite old now, but it's quite a good comparison. This is one I always like. We do have an awful lot of different formal methods. Z is one of them. I've mentioned B. There's others here. There's like PVS there. There's lots of different ones. And if you're in industry and you look at these formal methods floating around, it's very difficult. This is the poor industry person here looking a bit miserable. Trying to work out which one to use is very difficult. And we don't have a solution, but I think it's something that formal methods people ought to be working on more to help in deciding. And of course, the tools are very difficult to use. The formal methods tool in action. They're getting better. So, but if you go into industry with tools and you show them some academic tool, that's not going to be of much interest to them. You've got to have something really robust that looks impressive. Got a good user interface and so on. So over the years, there have been various books, some by me, some by others. I mean, I've got to race through these, but this is sort of the situation 15 years ago or something. Various examples of formal methods being used. Later, some more examples. So there are all these different examples floating around, which we're trying to capture some of these in books to say, formal methods are being used. And I guess, probably, although everyone maybe slates Microsoft somewhat, they're probably one of the bigger users of formal methods now, because they've had problems with software over the years. And they realise they need to improve, and they are doing a lot of formal methods stuff around the back, perhaps not being called formal methods, but it certainly is a formal approach. And there are some recent books, I just thought I'd do a quick check to see what's around, so people are still doing examples of formal methods. So that's a little background, slightly historical intro. Now we're going to get on to the main part, which is an air traffic control project that I've mentioned that I was working on that's used Z to to do quite a large project. It's about 150 people, so I guess not mega size, but a reasonable size. And the customer is NATS. They have a lot of flights, a lot of people involved. They want to keep them all safe and so on. That's over 3 times as many people in the country passing through. There are various air traffic control centres, and the one this particular project was working towards was Swanwick. So even around Europe, I'll show you later, there's a lot of different air traffic controls, and they're all separate. There are obviously lots of airports, and they all have their own separate air traffic controls, the local control. So this project was to do air traffic control in England and Wales, essentially. So this is the NATS centre in Swanwick. You can see, I guess it looks like a sort of ordinary building, but it's pretty well defended, because you don't want your air traffic control going wrong. So it's got lots of different electricity supplies coming in. It's terrorists come in. There's things, it's pretty well built to stop that. The whole thing burns. It can keep going for quite a while, and so on. There's a room full of batteries. If all the electricity goes, they've never had to use those. But at the inside, I guess you can see it's just a lot of screens. And we're looking at there's a local screen, and actually until this project, they were still using, you may be amazed to hear, real flight strips. And that's one flight strip, so this is just a test to see if there are any real air traffic controllers here, bar anyone on the project. Does anyone know which flight strip this is?
I can tell you it's got Heathrow at the bottom there.
Okay, good. Okay.
JFK, presumably.
JFK, yes, it is JFK, yes. So I guess the clue is probably Conk. You may have heard of an aircraft called Conk.
And speed for that is a good.
So this is actually the last flight, which I was quite interested in, because it used to fly over our house twice a day, and all the beams used to shake.
Yeah.
Now it's a bit quieter. So they did actually give me a genuine quotes flight strip for the last flight of Concord, but an awful lot were printed for the last flight. But it was a genuine one printed for the last flight.
Which bit said Heathrow?
Yes,
Echo Golf Lima Lima, the bottom right.
Oh, obviously.
They're different codes to the ones you use for your baggage. That's what's confusing me.
Yeah, certainly.
Anyway, so it's air traffic control in Europe. So yes, you may wonder what's going on here. Well, the first time I gave this talk was in New Zealand. Slightly differently to us. So, but I kept it in, but for you, I'll tell you how. So you might make a bit more sense of the European airspace there. You can see it's pretty complicated as well. Well, you can see over here, this is the air traffic control we were working on for London. You can see Scotland above, Shannon, that's Ireland. So hopefully you can start working out Lisbon, Portugal, etc. But you can see it's quite a lot of different sort of sectors, if you like. And as you fly around Europe, you're being passed, as you go over any one of these boundaries, you're being passed from one to another, moving from feet to meters as you travel through. That's one thing we have to spend a lot of time on as units, because that's quite an issue. So you can see this project is actually doing quite a small part of even the European airspace. Obviously, they probably hope that they'll be able to interest other people to use the same software.
So, what is the detailed picture?
This one, that's just London. I mean, this is off Wikipedia, so they just had this in Paris.
But they're not the same areas, are they?
Well, it's this area here. So
oh, I see. It's a blow up of that.
So this is the bit. There's Manchester, obviously. So it's blended up, so you can see a little bit of airport traffic control there.
Yeah.
So, I guess NATS have a sort of lowish profile. But you see it every so often. If you go around Heathrow, a sort of advertising sign here, they've got NATS, so it does sort of appear. And you saw how complicated that was, and how you might think now we have the European Union, so it will be unified. Well, they are talking about it. So there is this project called TISA that started in 2004, and it's due to finish in 2020. So where they might, well, the aim is to try and unify the European skies a bit more. We can see it's a very long-term project, and they're only about halfway through it. So I don't know what's going to happen at the end of that. So I mentioned that this is going to talk about some industrial work. When you work in industry, you have to sign non-disclosure agreements and you have to get things agreed. So the slides in the middle here are actually slides that have been agreed by the customer, originally prepared by Neil White, who was one of the engineers on the project. So just a quick overview of the project. It's called IFAX. Nobody can ever remember what IFAX stands for. One thing you find in industry is when you arrive, there's so many different acronyms flying around, and everyone knows what the acronym is, but nobody actually knows what the acronym stands for. So it's just an interesting observation that I noticed when. So anyway, it tells you what IFAX is in a slide or two later. The main part of the talk is going to talk about Z, so there's a lot of specifications that are written on this project. It was implemented in Spark. I'll talk just a little bit about that. And I guess the most interesting part, I think, is actually the fact that they were using the Z to do the testing. So that was the main idea of having the Z, not to do proofs, but actually to have something you can test against. And normally when you do testing in industry, when you write a program, but you don't really know what the program's meant to do, so you put the figure in the air and do a few tests you think are good. Whereas here, it was very formal, I guess, in the non-formal meaning, but a rigorous approach to actually deciding what tests you need to do by looking at the formal specification. And there was a little use of Mathematica as well, so I'll come on to it. So anyway, NATS well, it's really the air traffic control services provider. This is what the airspace looks like within that European map that we saw. So actually, it isn't just one big area that you can fly around. Basically, you have sort of almost like motorways, tubes that you're allowed to fly through in the air, and they've been allowed. Basically, the whole of airspace is actually military airspace to start with, and they generously allow civilian aircraft to fly, in various parts. But you have to follow the rules, and they can change at any time if there's an emergency. And you can always switch back to being military airspace. The Queen flies anywhere, all round her becomes military airspace automatically. You navigate there. So things can change, but that's what it essentially looks like. Obviously, things are complicated around here, and this is all under London control. But once you're going out on one of these sort of highways, if you like, then that's part of this air traffic control system. And you see, actually learning all the different parts of this, if you're an air traffic controller, you get to learn. Even these are all divided up into sectors, and you get to learn that particular sector and its geometry, and you know how to get planes in and out of that particular part.
And what happens if you need to fly outside of those corridors?
Well, I recommend not.
No, but I mean, for example, there's a perfectly good airport at Newquay down in Cornwall.
Well, this is all at certain levels, so if you lay down, things are a bit different. So we're dealing with high up, 22,000 feet up. So
okay.
yes, low down, you can get away with a lot more things than you can.
Well, down, you don't even need to tell anybody. If you're in the uncontrolled airspace, you just fly an aeroplane.
Where the yellow crosses the green and blue, I assume that's at different heights. Is that
well, there's some traffic lights in there.
Is it like a flyover?
No, I'm not absolutely sure. I mean, yes, you obviously do keep things separate. Whether they, sometimes there's more traffic one way and then you let the traffic the other way. I'm not absolutely sure because I'm not actually an air traffic controller. Okay.
I think maybe some of the colours are. I think they've got names which are those colours in some cases.
Yeah.
Amber 1.
Right. Okay. Well, it does say console control Well, there's various. Some of these are, yes, obviously local control sensors as well. So this is what an air traffic control team look like. Actually, this is pre-installation of the new stuff. I'll explain the differences. So there's 3 people in this team. There's a planner, and you can think of air traffic a bit like the internet. So you've got all these planes flying around, and of course on the internet you get given packets, and you're trying to get rid of them as quickly as possible to somebody else. That's how the internet works essentially. So the planner takes some of these planes in, and then also deals with getting rid of them again onto the next person. And you can now up to about 6 or 7 planes being dealt with by this team. So you have to be very good at sort of video game 3D, being able to understand where 6 different things are flying around, if they're going to hit each other, etc. So that's what the tactical control will be doing. Once it's been given a plane to deal with, they know we've got to get it out again. How are we going to get it out? What route are we going to ask them to do? That's what the controller does. And well, in the old system, you had a system doing flight strips. So of course, I've told you, flight strips is one thing that's been made for electronic. So I guess this is where unions get involved. You know, what's this person going to do? So obviously there was all that side of things to deal with. But actually, the air traffic controllers really like the system because it gives them a lot of extra information, as well as getting rid of the flight strips. It gives, and as well as, in addition to the sort of standard information they previously got, there's a lot of other information that they're now given that helps them make decisions. So, okay, it's interim future area control tool support. So, presumably at some point interim will disappear. So, as I said, it's replacing these flight strips is one thing, which is a relatively small thing to do. But the more interesting part is coming up with these trajectory tools. And there are various different ones. I'm going to show you one example just to give you a flavour. But they basically, previously, they literally had to hold everything in their head and look at this 2D map of what's going on in 3D. Whereas these trajectory tools give them extra information, lets them look ahead more. I mean, I think you could only look ahead about 5 minutes previously, and this lets you look ahead 15, 20 minutes. So it gives you, a lot more control about, I guess, these planes, something might be happening, to do something about it. So it's not an air traffic control system, in that this system doesn't tell the planes what to do. This is just something to aid the air traffic controllers. They look at it and make the decisions and then tell the pilots. I mean, of course, this whole thing could be totally automated and you can just send messages to planes saying, do this, get any pilots. Most of you probably wouldn't want to fly on planes like that, so it's not acceptable. So this is one example of one of these tools. So this is a separation monitor, and I suppose you can see you've got time to interaction here between 0 and 15 minutes. So this is looking at pairs of planes and what might happen to them in the future. So this basically, up here we've got separation. So this line's 5 nautical miles, and that's the separation you normally want to keep between planes. So if you want to think of this as a video game, essentially you're trying to keep all planes above that 5. So you've got 2 here in bed. Obviously you need to do something about it. If it gets down to 0, 0, well, hopefully you can see that's a disaster situation because you've got 2 planes in the same place now, and they're crashing. So obviously looking at this, this is the nearest to 0. We want to do something about this because they're quite going to be, if we don't do anything, they're going to be within 2 miles of each other. That's something we want to avoid. So the air traffic controller seeing this will first look at this and decide what are we going to do to get that back up into this safe area. I mean, this one is only just within 5, so it's further away, so we don't need to worry quite so much.
Is this horizontal separation or what?
Well, yes, again,
You're simplifying it.
Yeah, I'm simplifying, yes.
Yeah.
Obviously, you've got different levels. Typically, you have planes at different heights and so on. So, yes. but I think hopefully it gives an idea of the sort of things they've got, which previously, you can't calculate that sort of map in your head. You're probably, you might just about be able to think of something very close to here, but anything further out. So that means they can actually start dealing with things much earlier on, which means actually you can take avoiding action without changing the planes too much. You can save fuel. So one of the big things about this is it actually saves money. You need less fuel because you have less panic situations because you've done things a lot earlier on. So looking at the Z part, people can put their binoculars on that. So the IFAC spec was, the functional spec was done in Z. So, and there's thousands of pages of Z, so it's a pretty big Z spec. I mean, obviously there's some structure to that model, but actually the biggest part of the system was, over 1,000 pages. So that's a significant size Z spec. Some of the algorithms were specified with maths, so where you just want to do differential equations and so on, some of those calculations of paths and planes and so on, doesn't make sense to use Z, just use normal maths for that part of it. For the human-machine interface, typically you're sort of, if you're in one state, you do something, you want to go to another state, well, they were just specified as tables, which is fairly, they're literally, when they're implemented, they go into arrays in Ada, so it's fairly simple. And of course, there's a lot of English, so actually the Z spec, just like we always recommend with Z, at least half of it was English in amongst that 1,000 whatever pages. So it was quite, there were obviously guidelines to follow, and they certainly followed the normal Z guidelines, having a good amount of English, which was actually liked by the customer. Some of the customers could read the Z, some couldn't. So the idea was you could actually read this document, and even if you couldn't understand the Z, you could still read the English part. So yes, this is where you can get. So that's a typical visual Z. That's probably one of the large. I mean, most of the schemas are probably a bit smaller than that. Some are larger. I mean, no schema was more than a page. Normally, you wanted, say, a quarter of a page maximum for the guideline. But anyway, you can see a bit of English there describing things in standard Z style with various predicates as well down there. So, one big issue in industry is training. So, and they realise actually that reading Z is a lot easier than writing Z. It's a bit like reading a novel and writing a novel. Hopefully, most of you can read one, but you might think twice about writing one. So most of the people on this project only needed to be able to read Z, because actually the spec team was relatively small to write Z. There were an awful lot of testers and programmers and so on who needed to look at the spec, understand it, and do whatever they needed to do. So you can see that they have a 3-day course. They say towards the after a week, probably optimistic, but then these are good software engineers. So certainly the people, they have contractors as well as their own staff, and the people doing the Z part were good software engineers. So they trained up 75 people to read Z. Fortunately, I was one of the people who already use Z, so I had to do some of the training as a result. But interestingly, they also, some of the air traffic control people, domain experts, people from the customers team and so on, they all learn Z. Well, some of them also learn Z. So because NAPS was very much involved with the project as well as the culture and practice. So there is a Z writer, of course, as well. These two courses are things that Praxis, or Ultron Praxis now, do anyway. You can go and have a Z course there. So they're using it on the project to train people for this project. Most of the people who are already at Praxis, lots of them know Z anyway, and have used it for a long time. So they have another 3-day course which you might do in addition, and they say 3 months. as an academic, I might double these numbers and say 6 months. But, certainly you're doing, after a few months you're doing, but you can see 3 months is an awfully long time in industry to get up to. So, most industries are happy if you can do something after a week, but if you say it's going to take 3 months, that's one of the problems with formal methods. They say, well, that's too long, we haven't got time to do that. In this case, they're able to do it because the company practices one of the leading formal methods companies already. They've got people trained up so they don't have that 3 month problem. Because if you're starting from scratch, that's a really, really big issue.
Excuse me, can you tell me what you mean by fluency in Z? In other words, how much of Z are we talking
that's
about?
why I say 3 months, I'd say 6 months. So yes, it depends what you mean by fluency. So I don't think there's an absolute definition of fluency.
Sure. And if it's just sets and partial functions, for example, then.
Oops. Yeah. They learned a reasonable amount of Z. No, I don't. Yes, maybe they didn't let DAX or something.
Sure.
But no, this is learning Z. So yes, not a restrictive form of Z. I think the main, if you use anything like Z, it's like writing English. The first time you write an essay, you look back at it a month or two later, and that's rubbish because you improve. Well, it's just the same when you learn Z. The first things you write aren't wonderful, but then you get better at it. So it's no worse than learning a natural language. Perhaps better.
Well, I was going to compare it with learning some other programming language.
Okay, yes,
but you don't become fluent in C++ in 3 months, surely.
Okay. Well, that's why I say 6 months. Depends what you mean.
I don't know. Typically when you read the job adverts.
They mean we can charge a customer first.
Yeah.
That's an industry definition of fluent.
But when you look at job adverts, 2 years experience in C programming or something would be considered the sort of qualification you might look at.
Remember, I would say these
Or
people are
Java
the top, might be top 10% software engineers. So these are good engineers. One problem with software I always think is that the good people are 10 times as good as the bad person, and the good person only costs twice as much as the bad person. So actually, you're much better off paying people twice the salary, and getting a really good person who's going to do a really good job and probably 10 times more productive than that half-price person. That's one of the problems with software metrics and so on. You get things like that. It's not like putting rivets into a ship where you can just count the number of rivets and say it's going to take so long because the people it's so people dependent on the project, and our practice just make sure they get good people in projects like this.
Yeah.
So yes, you'll be interested to know all the Z was written in Microsoft Word because although any real Z person would of course use LaTeX, which I guess any real industry person wouldn't normally use. So yes, in real industry you have to use what real industry uses, which is Word. So yes, all these thousands of pages were in Word. You might be amazed to hear, but it still worked. It might be slightly clunky, but it wasn't a huge issue. I guess one good thing was that Anthony Hall has actually written a very nice tool to go with Word for type checking, which any of you have to write Z in Word, then it's a really good tool because that basically converts the Word back into LaTeX, plus the type checking rules standard. But then, very cleverly, then works back again and works out exactly where in the Word document that LaTeX line was. So it does actually point to where the errors were. So it's one of the nicer tools around for Word, and that's a very, very important part of this project. Because even just type checking, that does an awful lot of checking. If something that's 1,000 pages long, you can find an awful lot of problems just through type checking. So these are advantages and disadvantages of written by a real industry person rather than me. So, as I said, this is by one of the real engineers. So they certainly like the fact that you can put the English and the Z together in documents. That works very well. Because also with these other formal methods, you have sort of separate bits, mathematics and English, and trying to relate the two can be difficult. So yes, the errors, getting the errors back in the right place, that was a very important puzzle. That's all I just mentioned. There also another part of the tool was just doing cross-referencing of all the Z names, all those schema boxes and names. You know, you've got thousands of schemas. You see one reference somewhere, where is it? So literally, you can press the thing and it will go to the right place in the document and find whichever it is, as well as producing a normal index so that you can look at them on paper as well. So yes, okay, disadvantages, yes, so large Word documents are a pain, but still possible. So they can be, you know, when you have a 1,000-page document, as I mentioned, it can be a bit slow, but not unbearably slow. So it might take a few minutes to do your type checking, but it's not sort of hours. So it's sort of a cup of coffee rather than a lunch, and a good lunch.
Not a French lunch.
Yeah. Another issue is branches, which so on a real project like this, you know, you've got different people working on different versions of the software, the spec, and so on. So the spec people are coming up with some new things, and they've got different. Maybe some bits are going to be included, and other bits not at different stages. And then eventually, of course, well, you've got the programmers and the testers working on slightly different versions. But eventually, you want it all to come back together again. So that actual merging part can be, well, they did have, you know, things in Word that helps you do it, but it's still not perfect. I guess one issue they had also, obviously, there's that Open Office versus Microsoft Office, and they were actually interested in using both because sometimes one was better than the other. So it's just a practical issue. So I mentioned state machines. So actually, the spec for this, although you could write this in Z or anything else, it just really wasn't worth it because essentially, you know, if you're in one state and these states might be their schemas, and you're going to move to another state, another state schema. You know, so when you press a button, something's going to happen. So literally, you know, you can use a matrix or a thing like this to actually say this is what's going to happen. And that just maps straight onto an array in Ada, for instance. So training for that, well, hopefully even you can sort of see. I've just given you the training, okay? So you're now all experts in that. So there weren't even any tools. You could imagine having somebody that automatically took one of those and made the Ada array for you. So the Spark. Well, Spark Ada, which I was less involved with, I was involved on the Z team. But Spark Ada, if you don't know, it's an annotated subset of Ada, which is the safe bit of Ada. So Ada with all the difficult bits, taking out the bits that have semantic problems. So, and that means it does have things like various tools for doing proofs and so on. Which weren't used on this project, so I'm not going to concentrate on that. So actually, although Spark Ada was used on this project because the practices know it well, you know, and they've got people trained up to program in it, they didn't use any of the proof tools with it. So it's just done by programmers looking at the Z spec. They've all been trained to read Z and then programming. And actually, you know, if a programmer knows what they're meant to do, they're pretty good at doing that. Normally, the problem in the industry is programmers given a bit of English and a few diagrams until we go off and program something. I think that's right. But it can be like that anyway. But here they did actually have a formal definition of what was needed, and provided they could read that formal definition. Actually, that transition is, you know, obviously you can introduce errors, but a lot of errors were introduced. So you probably can't see this much, but I mean, you can add things like assertions to say this is what we want for this stage. And so in your annotated, these are the red bits of annotations. So, and on smaller projects where it's more feasible, you know, they do proofs. As I said, it's a big project. It's just not feasible on this, not cost effective.
The assertion there, is it just a comment or is it actually
basically it's meant to be a comment so that a normal Ada compiler doesn't know that. Assertions will ignore it as a comment.
But there's a tool that reads
Yes,
that.
there's a tool that will look for this hash, comment hash, and then use those. So it's a sort of slight trick.
Yeah.
Just means that it's all backwards compatible with other non-proof tools. So, well, slightly fewer people were trained to do Spark, because only people doing the implementation needed to know about Spark. And I was, as I said, I wasn't on the implementation, so I've never been on a Spark training course, obviously. It looks a little bit. So, and most of the people doing this were contractors. I mean, actually, this project was bigger than the company, you know, so there were a lot of contractors involved, but also a lot of people from the company. So, you know, people might have, so they have quite diverse programming background, because I guess if you get a contractor, a lot of them won't have done Ada, they might have just done, you know, Java, as I mentioned, whatever it is. I mean, to an academic, it's all the same, it's all just imperative programming, just with a slightly different syntax. If you're a good software engineer, you know, if you've learned one, it's just a slightly different dialect. So the coders had to be Z readers, because that was the spec, that's what they're meant to be coding. So they've all been on the Z reading course. And they say that, you were saying it takes a while to learn to code, they're saying they learn quickly, but these would be people who would already be very good programmers, would be learning Spark Ada as just another syntax. But if you want to do proofs, well, they say 2 months, so I would double this for 4 months perhaps, but they won't do that anyway. So there is a tool set, which I'm not going to really talk about because it wasn't used on the project. But perhaps the most interesting part of the project, I think, was, you know, okay, we're using formal methods, and the real use of that Z spec, as well as doing the coding, was actually to do the testing. So the test team was even bigger than the programming. It was the biggest team of the whole lot. Spec team was quite small comparatively. So the testing team were busy producing a lot of documents like this, which again you can't read much, but essentially looking at the Z spec, partitioning it up. I mean, there's fairly standard ways of partitioning. So, you know, if you have to do this or do that, and you want to test this or that. So there's sort of standards that were produced for the project to say how you should do this partitioning. Some of it was, you know, used engineering judgment. There are quite a lot of standard rules to follow. And so you come up with various test conditions. So these are sort of Z style predicates here, saying what we're going to test. And then, you know, you might end up with things being true or false. So you have sorts of dots, depending on what you're expecting to happen for that case, or nothing, you know, it's arbitrary.
But how are these produced from the Z?
Manually.
Manually,
yes,
by reading the Z.
There's a huge team of people reading the Z and producing this document. There's no tool at all.
That seems strange.
Well, it'd be nice, I suppose it'd be nice to have a sort of first pass that took Z and did some partitioning, but there is no such Z tool as far as I know, unless anyone has produced one.
But
it would certainly be a useful Z tool.
You're presumably arguing that it's feasible to do that.
Well, it's not. You're not going to be able to do it all. You're still always going to need an engineer to do the difficult bits. But certainly, you could do a first pass and say, "Okay, I've done this. You know, all the sort of relatively easy parts. You need. You know, it's going to be heuristics. So there's always going to be another heuristic you could add to say you could do this automatically here. Like proofs, you can automate a lot of proofs, but there's always going to be a little bit you can't do.
I seem to remember a long time ago now that there was a long discussion about the fact that it wasn't possible to test every part in a program because the combinatorial explosion was just too big.
Equivalence classes. So you say, right, if something's here, we can on one test to do this, and we're going to assume that, you know, that means that that part of it is being tested.
So that thinking was all in it.
Yeah, yes.
I see.
So, well, there's just one example of where they'd. I mean, if you did just take the brute force program approach to doing this, well, he says this would end up with 1,000 things you might want to go through and test, which they're not going to really want to do it in reality. But if you have a good engineer working on it, working out orders to do things in, what makes sense, what doesn't make sense, then you can get it down to quite a reasonable size of test scripts. So obviously, a lot of testing you sort of do, you do this test, then you work out, well, then we can do this test immediately. Because most tests you're trying to get into some state do something and try and check the state after that is correct. Well, a lot of those states, you can join them together and do it. So, you know, a good engineer, and that's what you'll be thinking about. So, yes, there's a lot of initiative in that part of it, with needing good engineer judgment.
But surely that could be automated, because what you're describing conceptually is
So potentially,
how to stick together two states diagrams.
Yes, but there is no tool at the moment.
Okay.
So, and I would still say there's going to be cases where you need an engineer, but yes, I agree. But, so I'm throwing out some ideas.
Some challenges.
These would actually be much more useful tools than a lot of the tools formal methods people are doing at the moment. Because most formal methods people are doing all these esoteric proof things, where it's just something that actually did some of this initial partitioning would be a really useful tool in industry. But I guess it's a chicken and egg thing that there's enough demand, etc. Like if you go to your bank manager and ask for £100,000 to develop one of these tools, you might have trouble convincing them of the market, etc. So. This bit I'm going to talk about now is the reference models for the mathematics. So all the algorithms, which is the bit they really want to protect. Unfortunately, I know nothing about, so I can't tell you what the algorithms are anyway, which is a good thing. But they're specified in mathematics, differential equations and so on. But they need to be tested, just like the Z things needed to be tested. So these were tested mainly by doing it with reference implementations using Mathematica, because Mathematica, you can just write the mathematics down very directly in the Mathematica tool, and then you can run that Mathematica tool in parallel with your program.
Your code.
And see, it's going to be real numbers, so you're going to have to allow a bit of latitude, so you have to decide what, it's not going to be an exact match, so you decide what's the maximum sort of area you will allow. So that's engineering judgment. But that's how that part of this particular testing was done. So the Mathematica team was relatively small. There were only 5 people trained in Mathematica. Interestingly, the reference model had, if anything, there were as many problems in the actual reference model as the actual coded, which you might not have predicted. So of course, when you get a mismatch, even with the Z and program mismatch, but it might be the program that's wrong, or it might be the Z that's wrong. You have to find out. It might be that both are wrong, but normally it's. But even in the Z, and actually often, for instance, in the Z, the programmer might do something sensible and say they didn't really mean that's the Z, it's what you should do, and then you can correct the Z. Which might only just be something like brackets in the wrong place, on precedence or something. So anyway, it's a very small number and you can't really draw too many conclusions. So anyway, the contention is formal methods are being used all throughout the life cycle here, from spec through the coding through to testing, and even at the maintenance stage, which is obviously they're in the maintenance phase now. The Z spec is being maintained, so if there's a change, then people are actually keeping with the step. That's the idea here, that they are kept in step. So training engineers, as I said, is a barrier. I mean, it's a barrier one-off. So once you're over that barrier, you can practice well over that barrier. So that, in fact, one of the few companies that uses formal methods, even when the customer doesn't say you have to use formal methods, because they know, they know how to do it, and they're going to produce a better result, and you can do things often quicker. Do the testing is going to be less problematic, etc. So it's tools is the big issue. I mean, the Spark Examiner is quite a nice tool, but the Z tools that are coding aren't particularly wonderful. So if people have suggested tools that'd be nice to have, please do go and try them. They'd be great. So I'll just add a little. How long have I got?
You're fine for a bit yet.
Okay,
yes.
There's only a bit more, so this is just sort of, we're on the downhill. So just a few extra little things. I mean, another interesting tool they did use was a tool called DAWS, which is very helpful in tracing, because a project like this, you've got a huge spec with all these different schemas and obviously and all these different tests. Well, when you write an academic paper, it's very easy to check this and all this stuff and the other. If you've got thousands of pages, it's very easy to miss things. And so you want some sort of tool that's going to help you say, well, if we've got this spec or this schema, has it actually been tested? So this tool actually helps to demonstrate yes, at least everything has a test associated with it. It may not be necessarily the right test, but you haven't just forgotten it. That's a very important part to not forget anything. And it's got some quite nice visualization, of connections of schemas and so on. I'm always interested to find some of the visualizations in the middle of it that would say true or false with lots of arrows going in. I'm sure you'd enjoy that. So they have been doing, there have been little further developments on IFACs even up until now, and there's obviously been the maintenance. The main part of the project is basically over, but there have been other projects looking at, well, this IFAC's only looked up to about 15 minutes or so ahead. So it'd be nice to actually look much further, hours ahead, to actually start to do some planning. As I said, a lot of fuel is a really big cost flying aircraft, and you actually do some planning to make sure you're going to fly all these aircraft in a sensible way, minimise the fuel costs. So another possible, well, the forecasting tool they've been working on it. Again, I only have to say what's on the web. This is what but it's something that actually looks 4 hours ahead, and you do some planning over that sort of time scale and optimise the traffic flows. So just a little bit of reflection. So this is a quote I like because it's the first quote about email. Actually, that's the reason why French can't use the word email. They have to use courier because email actually means enamel in French. So still talking about sending an enamel. But anyway, this says that you can, if you do things in using things like marble, enamel, and all these difficult things, then you actually get a better result. And I would contend that formal methods may not be particularly easy, but they're going to come up with a better result than using just a bit of stuff. Plastic and whatever it is that makes people do. And this is just a little joke at the end. You should always be a bit careful with people selling Zs.
I've seen that.
You've seen this. That's all the methods people have seen this. Anyway, I was walking down Oxford Street and I looked in the window of one of the shops and it said Preparation Zs. And I thought, well, Zs on Oxford Street. Anyway, so I went to buy this thing called Preparation Z. It must be good. But then I sort of started reading the small print, so it had all these things that you have to worry about when you're going to use this Z stuff. So in particular, it said that this Z was being sold as a novelty item. So yes, you should always be a bit careful. Obviously, if you start using things like formal methods, you can't expect it to do everything for you. It's something you're going to commit to, put some effort in, and you'll get some results in return if you put the effort in. Anyway, thank you very much.
Thank you, John. Well, I'm sure there are going to be questions.
Jonathan, you were using fuzz, but you weren't using any Z animators.
No. Well, I have Z animators in academia, but I guess the problem with Z animators is they're not very efficient, and if you've got 1,000-page Z, then it gets a bit. I mean, the one thing they did do a little bit was there's an alloyed tool somebody made, which is sort of Z-like. So, and it's very nice, quick coding with alloy. So there was a little bit of sort of trying things out with alloy. Okay, this is a bit of Z. We just want to check it all works as we'd expect. So if you code it up in alloy, then you can very quickly see it's doing something sensible.
You didn't try Zans or Jazz?
No. Well, I don't know what the state of Zans is now. I mean, it's always a bit dodgy. Yeah.
It sort of stopped being developed.
Yeah, well, exactly. It's an academic toy. It's a novelty item.
Yeah.
No, so, I mean, it's a useful novelty item for teaching. I've used it for teaching, but in industry, I wouldn't say. So that's one thing, as I said, in industry can be a bit confusing. You think, well, there's all these different tools. Which are the ones I want? And actually, to be honest, I think I would say don't use Z-ANS in industry because it is too much of a novelty. But it is good for teaching. When you're first learning Z, trying things out with it.
Do you know of any others apart from Z-ANS?
No, well, all the action now is in B and event B and so on. So, although, Z is still being used in C for real things, there's not really much action. There was the ZT community tool, Z tools project, and that sort of, it seems to have petered out. So it'd be nice if, I think if you were investing in time for tools with Z, I would say the testing side is the side which would be really good to have some good tools for all the things we discussed earlier. It would be very nice to have something that does something for you for the testing.
I've got 3 questions / observations.
Okay.
So perhaps
One at a time.
perhaps.
Interlead.
Okay, when you, then I'm going to come to.
Oh, sure. Well,
Yeah. Carry on.
just choose whichever is the most interesting question.
Or you choose one and I'll talk about the other ones afterwards with you.
Oh yeah, okay.
Or you
yeah,
can come back, do one now and we can come back if we run out of questions.
Sure, that's fine. First of all, you didn't say what data abstractions you're using, which is very often the most interesting part of a formal model.
Yeah.
So looking at the example, I imagined that you were going to then talk about how a region of space is represented as a set of points, which is something that can't actually be implemented in a programming language, but it's useful conceptually. And did you do that, or did you
not
have
personally? And as I said, I've signed my non-disclosure agreement. So actually going into details is something I can't do that.
Okay.
Easy. Fortunately, I don't actually know anymore. That's the question. So, but yes, ignorance is always a very useful thing in that non-disclosure agreement. So,
Okay.
Obviously there's other
But
things.
the general point about
yes,
data structures,
yes.
how would you respond to that?
In what
So
sense?
Or which data abstractions?
Data abstractions, yes, sorry.
Well, certainly that's an important part of it.
I mean, as we all know, an algorithm can be simple or complex.
Yes.
Well,
Well,
trivial or complex,
you know,
according to what structure
yes.
you.
Well, it's an engineering judgment, I would say. I remember I came in basically at the middle of the project, so I wasn't involved at the early stage when all these sort of things were being decided, and they would have been decided by Nats talking to people at Praxis, trying things out, seeing. Nats have got an awful lot of expertise already, so a big part of the project was, getting the expertise from Nats people and using that domain knowledge, see what's sensible. So most of the people on the project aren't air traffic people, including me, I think. So it was very important to have the Nats people who really knew about what air traffic control was. Obviously, they might get bogged down with detailed things, and hopefully formal methods people could be a bit more, look at it in a more abstract way. And the way I would imagine it would have happened is that they would have a discussion, practice people would come up with some abstraction, go back and discuss it with the other discussion at that level. Hopefully at that nice high level as I showed you in that thing, so you're doing it all at 25, a few hundred lines level before you actually then, okay, we've got something that's worthwhile, and we'll go on. But yes, I wasn't involved with that at that stage.
So do you want to do your other points?
Yes. First of all, it occurs to me that there's no way of visualizing the structure of a Z specification that is analogous to the way we can easily visualize the structure of an OO program using class diagrams. That's one observation. Or at least you didn't say that.
Perhaps I meant there was one line bullet point saying there was a visualization tool.
Oh, right.
So, which I didn't dwell on.
Oh, I see. Right.
But yes, there were huge plots of basically schemas and how it was all connected together, which I would say it wasn't particularly useful, but it was interesting, perhaps sometimes useful, but it wasn't a big part of the project, so that's why I didn't But no, there are visualization tools to do that. There's the one where I mentioned that it had true or false stuck in the middle of it with all these other schemes.
Oh, I see.
When you saw the whole thing depending on false, you know. I hope that wasn't an important part.
Okay, I think maybe the other question afterwards, because then I'll surely be others.
Yeah, go ahead.
It must be something. A very quick question first, and then we'll say something. Have they got rid of the flight scripts now?
Yeah, yes, but they can always go back to them.
There's always
a backup.
Yeah.
So if all the power goes, you know, they can get.
Yeah, and the telephone lines are still up.
Yeah, yes, exactly.
You were slightly dismissive about the choice of language, and I always knew the Spark aid. I'm surprised they didn't use the Spark. Is it, first of all, why didn't they go to regular Ada if they weren't using the Spark? And have you got any feelings about which languages are more appropriate? And also, at the specification level, you talked to us about Z, but you mentioned others. Given a free choice, what would you go for?
Well, the reason why Spark and Z were chosen here are because they're basically the house styles of practice. They've already got a lot of people trained up in Z. And so that meant that that issue of training up engineers within the company anyway was not an issue.
That's normally the reason we give for not using Ada.
Well, because
in the case of practice,
no, in the case of practice, and they don't use, well, I suppose they would, if they were told by the customer you must use Ada and not Spark Ada, they might. But you know, they stick to Spark Ada because that's what they know that's from. So,
and at the specification level, would you go for Z because there are more tools?
Well, on this project, you know, it's a big project, so I think Z, well, despite the tools, you know, if you use something like B, I'm not convinced scales up quite so well.
Okay.
They've got better tools, so actually the scaling, Z does scale, but you know, it's thousands of pages, even without the decent tools, is a real demonstration that you can use to successfully scale up.
Thank you.
David, another from you.
I just wondered how close we are to eliminating the program and being able to compile specifications.
No, not close.
No.
A long way away, I think.
And in fact, it's theoretically impossible, so it's not even worth trying. So.
Can you elaborate that?
Well, if you have
Prove it's impossible.
it's my job. No, if you've got something that's not executable, transforming that into an executable, you know, you've got a lot of choices. Okay, you can do use heuristics to do some choice, but then it may be a very inefficient thing. You know, you've got to put some then. You know, there's always going to be another heuristic you need, which is the engineer coming in. So you can get a certain way of doing it, but there's always going to be something you can't do or haven't thought of.
Yeah. So another, can I just butt in on that? Because another way of putting that is that you could, in principle, have a Z virtual machine that would run it.
Well, you can't. Well, you can't run, well, Z is non-deterministic, so if you quotes run Z, when you've got a spec, and you know, a lot of different things could happen. So you've got to make a decision. Well, you can have a computer making a decision. We'll choose one of them, but it may not be the most sensible thing to choose for efficiency reasons or whatever it is. So there's always going to be something. That
okay. So this is a good plug, good moment to plug the fact that we normally go to Champagne Charlie's wine bar, which is underneath Charing Cross Station after the event. And if you want to continue this discussion, and Jonathan is free to come along.
Yes, before too many champagnes. Yes.
Exactly. Well, it's usually red wine.
Oh, right. Okay.
That might be a good time.
Sure, for industry.
Right. So anyway, your question.
Yes.
For the Z uninitiated,
yes.
Are there any tools for checking conformance between the Z specification and, for example, Spark Ada, in the same way that you have the news sort of suite of software model checking tools?
Well, not.
Maybe it's something you would never want to do. I am an uninitiated person to Z.
No, I mean, obviously, you know, you've got these tests, but you know, the Z doesn't produce. I mean, with Mathematica, for instance, you can run Mathematica is an executable specification language, so that is executable. So you actually get an answer out, and then you can, you know, run your real program that's much more efficient and get an answer and compare them. Well, you can't run the Z in the same sense because it's not executable.
But can you check if the implemented Spark conforms perfectly with how it's been specified?
Well, in a word, no. Well, not. I mean, you know, as I said, you can automate things to a certain extent, but there's always going to be something you can't do. So, I mean, for instance, with the B tool, a lot of that has proofs, and a lot of the proofs are automated, but there's always a certain percentage that you can't automate. And actually, one of the important things when you're using something like that tool is, for instance, maybe you can automate 90% of the proofs, and so you've got 10% of the work to do. You've got to do it by hand. Well, once you become better at B, you learn actually there are ways of writing. You can automate 95% of it. So you halve your efforts, and you have to do 5% of the proofs. If you get even better, you can gradually ease it up. But there's always going to be that little bit with proofs. There's always something. You know, on a new system, there's some, you know, you can add heuristics to do things, but there's always going to be something, except for simple, you know, if you're doing some linked lists or something, you know, but, you know, the real system is always going to be new.
Did you have a question?
Yeah, I was just wondering something towards the end where I was thinking the main airlines operate on a schedule that is sort of repeats on a weekly or daily basis.
You hope so.
Well, or so it would seem.
Legendary, as they say.
No, I just wondered if there's any history or learning of what were good strategies for.
Yes, I mean, it's an interesting idea, and I don't know whether I'm sure they must do recording of things. Not an aspect I've been involved in. Yes, because you know, if you do have a crash, you want to have the black box report.
But you know, an air traffic controller might say it's Tuesday. There's this flight coming in. Last week I did this and it worked very well.
Yes.
You might imagine.
I don't know how, because I mean, I think there's enough randomness when it comes to that. You know, this flight's be delayed by 5 minutes.
Yeah.
It's never going to be exactly the same each time. So I think you always, I mean, okay, you know, some things are going to happen the same, but I think I'm surmising.
Slot reservation sort of does it for the airports, but not for the airways.
Yes, well, you know, there's always something. The passenger hasn't got on; they've left their luggage or something. You know, so the plane's delayed. It's the wrong order. Okay, if there were no passengers involved, then yes, we could all take off at the right time.
It's notable.
But I think well, there's the weather as well. Yeah. Yes, I mean certainly that's part of it.
Way, headwinds, tailwinds.
Yeah, yes, I mean, yes, exactly. This part of this has got putting the weather into it as well. So that's not is certainly not very.
So the regularity is illusory.
I think so. Well, I don't know exactly how much is regular, but I think there's enough irregularities.
Yeah.
Yes,
I'll be at the back, and then I'll go to you.
Is there such a things like good Z style and bad Z style?
Yes.
It's the same way as it is in programming.
Absolutely, yes.
Are there any complications around it?
Well, there's some. I've written a paper. There are some, but there could be more. Because certainly the process of writing Z is interesting. Because actually, when most papers you read them and you have this set spec that's appeared, you know, how did it get there? So I think a very interesting part is you start with a blank sheet of paper, how you actually create something like a Z spec. I've written, you know, I've written one paper on that. People have done things on that. And so on this project, for instance, there are guidelines for how to write the Z. Some of which, well, a lot of it is standard stuff like, you know, have some amount of English and other things. But they had some things that were very pertinent to very large specs, because as an academic, I didn't really have to think about it before you do a large spec. So just how you're going to organise that spec so it's not totally higgledy-piggledy. Well, if everyone agrees to conform to a certain way of doing things, then, you know, with a hierarchical structure and so on, then you can, yes, it's a lot easier to navigate your way around. But yes, that first 3 to 6 months, people are writing the bad Z, and you gradually learn, you know, nicer ways of doing it. And also, there's just different ways, like you can write an English sentence in a different way, you can write Z in a different way. Some people love quantifiers. I'm not so keen on quantifiers, and you know, there's lots of Z operators that you can use instead of quantifiers, which looks a bit more like for functional programming or something. So a lot of magicians may prefer quantifiers. It's a stylistic thing. I mean, we saw a few quantifiers there. There were quite a lot of quantifiers.
There were, yeah. Question down here.
Just a question.
Were formal methods used on all the software, or just the application layer? For example, I did notice there was some graphics there. So with the graphics,
Well, no, yes, no, I think the graphical side wasn't done formally. Yes, so it's the functional part. So most of the functional part was done formally. Yes, yeah, was it? Yes, the interface wasn't.
Which was, I presume, there was no OS in the system.
Well, there is no OS.
Sorry,
it's not Windows. That's yes,
Thank heaven.
yes, exactly. So that's as much as I'll say.
right.
Yes.
All right, last question.
Was it just plain said, or was it objects?
No, it's plain said. Yes. So, yes.
Okay, I'm going to give myself the last question,
Okay.
which is, what was the customer reaction at the end of the project? Did the customer feel convinced that formal methods had actually helped to get a better product?
Yes.
Or
Well, I wasn't there at the end. I was a bit contractor, so
don't cop out. Give me at least a clue.
yes, I can give a clue. I'm just saying I wasn't there. But essentially, I think the customer was very keen. All these new projects they're doing, so they're continuing and wanting to use. So yes, that certainly realised it's a good thing to do, and they're follow-on projects and they're continuing. So. And that's people learn Z, so they know Z now. With a new project, they can use those people, etc. So yes, from that point of view, that's they definitely haven't said go away. We never want to do done. Once again.
Okay, now you know why I asked that, because I was around with the IBM Pix product.
Right. Oh yes.
They were
Okay,
using
fair enough.
Not that I was
No.
didn't actually work on that bit, but I was.
Well, that's
very well aware
another
of that.
interesting case.
And I'll just give you that alternative experience.
Yes.
was
Well,
that
interesting. Your
having learned how to use formal methods, the conclusion in that project was we now understand how to design better. And now that we can design better, we don't actually need them to do it.
Well, in a sense, I think it's like learning Latin. I had to do Latin. I can't remember a thing about anything about Latin and Greek. But on the other hand, it means that I've got a sort of idea of grammar and things in the back. And doing formal methods as a computer scientist thing is very important, because then you go into industry, you may not write down the preconditions and postconditions formally, but you've got that sort of mindset in your head, so you can think about things in a different way than you would have with a more rigorous approach. So,
which is the bit
yes.
Yeah.
So I think all software engineers should have a formal methods grounding, even if they don't. Even if a lot of the projects they never use formal methods, or even if they never use formal methods, I think it's good.
If they never do a proof.
Yes. Well, I think they should have done a proof at university, but yes, not.
Right. So a quick reminder, can you please sign the attendance sheet if you haven't already done so? For those of you who'd like to go to the wine bar afterwards, you simply go along the Strand, turn down Villiers Street on the left, and a little way down there you'll find a turning to the right under the arches, and it's just the door. It's just there. I hope you can help us with this for a little while.
Yes.
And there'll be a group of people wandering that direction, so just follow us if you don't know where to go. And a big thank you to Jonathan for coming on.